So today we'll be discussing an energy balance problem that states that water from a 3-meter tall by 30-meter diameter holding tank flows vertically down a 7-meter length of a 1-meter diameter pipe into the bottom of a massive gold-plated jacuzzi through a 10-inch diameter horizontal nozzle. The water depth in the jacuzzi is kept at 1 meter by pumping water back into the tank. The energy conscious king wants to know how much power the 100% efficient pump requires. If the pump is perfectly insulated and transfers no heat to the water, is a chiller necessary to keep the water at the same temperature? So to start this off, I'm going to go ahead and draw what we're looking at. So up here we'll have the holding tank, and then we'll go down and it will flow into this jacuzzi. And so from there, we're going to have our jacuzzi that look like this. So this is the jacuzzi. And so we know that the water is flowing down here, and so we can say that this is the holding tank water. And we know that this is 3 meters. We know that this pipe all the way down to the surface is 7 meters, because the pipe's 7 meters in length. And then we know that this water here in the jacuzzi is 1 meter. And then we're having the water go back through a pump. So that'll be our pump. It's flowing back up into the holding tank and it's circulating. And so we'll draw arrows to show the direction. And so with that, we're given initial values. We know that P1 equals 0. Z1 equals 0. So our pressure 1 is 0. Our height difference 1 is 0. And then our velocity 1 is 0. And then we're also given that P2 is equal to 0. So our pressure 2 is equal to 0. Our Z2 is equal to -9 meters. And then our V2 we do not know yet. So with that, we're going to go ahead and we're going to take Bernoulli's equation. I'm going to write it out as a reference. So we'll have delta P, so change in pressure, over rho, which is density, plus gravitational acceleration, G, times the change in distance, Z, plus velocity 2 squared minus velocity 1 squared over 2. And that's equal to our power, which is Wn times F over mass. And then that's minus our change in velocity minus Q, or heat, over our mass. And so with that as a reference, we're going to go ahead and we're going to take this left side of the equation and we're going to plug in values. So we're going to have delta P, change in pressure, over our density plus our gravitational acceleration times change in distance plus our velocity 2 squared minus velocity 1 squared over 2. We're going to set that equal to 0. When we know that our pressure 1 is 0 and our pressure 2 is 0, so that's going to make this numerator 0 and make this whole term 0, so we don't have to worry about that. And so we're going to go ahead and we're going to say that G is times our delta Z, and we know that Z2 is -9 meters, and that'll be minus our Z1, which is 0 meters. And then that's plus our V2, our velocity 2 squared, minus our velocity 1 squared, which velocity 1 is 0, and that's over 2. And we set that equal to 0. So to simplify that, we'll have 9G equals, or 9G, sorry, not equals, 9G plus V2 squared over 2 equals 0. And that's -9, my bad. And so we'll go ahead and we'll add this -9 over to this other side. We'll be left with V2 squared over 2 equals 9G. Multiply 2 by both sides and then take the square root. So then we're left with velocity 2 equals the square root of 18G. And so with that, we're going to go ahead and we're going to use our flow rate equation, which states that the flow rate Q dot equals our area times our velocity. And so in this case, we know that our Q dot will be equal to, right, take our area, but we have to do a unit conversion. So we'll say the 10-inch pipe or 10-inch nozzle, diameter nozzle over 12 inches times 1 meter over 3.28 feet. And so that's just a unit conversion over 2, and that whole thing will be squared and then times pi. And then so that's our area, and then we have to multiply by our velocity, which is up here, our v2, which would be times the square root of 18g. And so from there, we're going to go ahead and we're going to write our power equation, which power is equal to Q dot times WNF over mass. And so from there, we're going to go back to our original equation and we're going to rewrite it. And so we'll have our delta P over density plus our gravitational acceleration times change in distance equals WNF over our mass. And so we'll know that WNF over our mass equals 9g. And so we can go ahead and we can say that power is equal to, I'll throw the whole thing in brackets, our unit conversion, so 10 inches over 12 inches times 1 meter over 3.28 feet over 2. And so that whole term there is squared, and that's times pi, so we have our area still. And then that'll be times our velocity, which is 18g. I'll close the bracket. And that whole thing is times our WNF over m, which would be times 9g. And so we'll go ahead and we'll plug in our 9.81 meters squared per second for our gravitational acceleration. We come out and we get that the power is equal to 59.4 watts. And power is measured in watts. And so we can compare that by saying that our WNF over m flows to our potential energy, to our kinetic energy, and then to our velocity squared over 2, which is all equal to our change in temperature times our heat constant. And so the second question of this problem says, is the chiller necessary? And that means the chiller necessary to keep the temperature the same of the water. Well, in this case, the chiller is necessary. So yes, the chiller is needed to keep the water at the same temperature. And the reason for that is because without the chiller, the energy in the hot tub would build up. And so the chiller is a way to release that energy that builds up. So same temperature without it, the energy in the hot tub would build up. Chiller equals way to release energy.